Okay, so Bismillahirrahmanirrahim. So we are now on this fifth lecture for the course. Actually, the title is not this. The title, we're gonna cover convolution neural networks today. Okay, so this title is wrong. Okay, I'll change that later on. No problem. So in the last class before the exam, we were talking about these parameters that we need to take care of in any deep learning application. All of these are meant to avoid overfitting, and overfitting can occur in deep learning because of the fact that we have too many parameters to learn. If you have a reasonable number of parameters, and the data is also not that much complicated like in traditional machine learning scenarios, then it is very improbable that your data will overfit, or your model will overfit the data, because you don't have that much to learn and the data is not that much कि वो overfit कर जाए. ठीक है? So in that case, there was no need to do regularization in the initial days when we were talking about the initial 2000s. At that time when we were using R and Python and other softwares. So even in those softwares, there was no concept of regularization. Now, if you take, I think, Vecka or RapidMiner, I think they have the regularization input there because the data has grown complicated. So in deep learning, the scenario becomes complex because of the fact that if you use a fully connected network, okay, so that really complicates things. Although the learning is very good, like we have seen for the backpropagation case, कि अगर आपका neural network fully connected है, then you are able to learn very complex scenarios like images of numbers and cats and dogs and other complicated things like text, etc., forecasting of time series. For example, one of the problems that we are working on right now with Khan is the prediction of mortality in real time. Prediction of mortality of ICU patients in real time. Okay, so in real time we are inputting maybe 25 to 30 or even more than that, maybe even 50 input variables in real time after every hour or after every half an hour, and you want the prediction of mortality after every 1 hour. एक घंटे के बाद, is the patient going to expire or not? So that's a very complicated problem, right? You can't solve this using SVM or you get the point, right? SVM mein you get this training data in which you have a classification label and you can apply random forest and SVM, and so it's not meant for real-time forecasting of data. So for these kind of problems, you must use deep learning models. So if you have visual images, if you want to work with images, then 99% of the people are using convolution neural networks because that is specifically designed for visual imagery. Okay, but it could have other uses as well. It's basically, deep learning is basically a feature selection mechanism. That's what you need to remember. कि deep learning के जितने भी scenarios हैं, जैसे convolution neural networks is defined by 3 specific things. Okay, so convolution, the subsampling, and their own activation functions, which are specific to convolution neural networks, but they can be used in other networks as well. So these 3 things are basically meant to extract the features from the images, which can help you do the classification. Image में problem ही यही है, everything is not relevant. So you need some mechanism to extract the relevant feature. Similarly, for the textual scenario, when you input a corpus of documents to predict the next sequence of words, or to predict spam, for example, real-time data and you want to predict spam. So in that case also, every word is not important to predict the next sequence of words. So I give you a corpus of documents worth, let's say 25 million words, and I want you to predict the next sequence के अगला बंदा क्या लिखेगा या क्या बात की जाएगी, या you want to predict कि मैं इसको क्या जवाब दूं if you want to make a chatbot. ठीक है, right? So all of those 10 million or 15 million words are not important to predict. Everything is not important to make a prediction. So what deep learning does is it extracts the relevant features through the multiple hidden layers. So primarily deep learning is in fact a feature selection mechanism. समझ में आ रही बात की? It's not something कि आप कहें कि meant for deep learning is not meant for classification. For classification, you already have the multi-layer perceptron, you already have random forest, like you have the XGBoost and other boosting algorithms which are working very good. So deep learning is basically a feature selection mechanism that is coupled with a classification algorithm. In most cases, it is a multi-layer perceptron or a neural network. So you worked with multi-layer perceptron, okay? So just make a perceptron or a with sigmoid neurons, ML. We call it the multi-layer perceptron, but actually we're using the sigmoid neurons, not the perceptron activation function. But usko कहते हैं MLP है, सही है, जो कि which is not a deep learning algorithm. So the problem of regularization arises because of the fact that deep learning uses more than one hidden layer, and that drastically increases the number of parameters to learn. It's easily in thousands. On the contrary, in machine learning, you just have 2 or 3 parameters to tune before you get the high accuracy or the high AUC curve or whatever. So that is why we have multiple strategies in deep learning to avoid overfitting. And mostly you apply almost all of them. For example, you apply the dropout rate, you apply regularization, you apply batch normalization. ठीक है, वो मैं भूल गया आपको batch normalization बताने से. I'll tell that in the next class. ठीक है. Early stopping तो is a manual process. Data augmentation is also your own choice.
Sir, is early stopping the same as
Early stopping, what's early stopping? Sorry, दोबारा बोलिएगा. Any strategy to, देखें, the point is that if you train too much, then it might overfit. So that is why you need early stopping. So early stopping में एक तो ये है जो कि standard method है, but you can also adopt your own methods according to your data set. ठीक है? So that is the main point that you need to understand about deep learning. Deep learning is actually a feature selection mechanism, and it works well because it selects features in such an excellent way because of the particular architecture that has been used. For example, recurrent neural networks, we are using the recurrence mechanism, taking input from the previous timestamp, and the previous timestamp is taking input from the previous timestamp. So I save a long series of historical timestamps to make a prediction right now. So through recurrence, I am able to save a lot of history. So the more I remember from the background, from the history, the better I can predict. So that is why LSTM and its counterparts are performing really good in forecasting tasks. तो अब आजकल इसमें स्टॉक्स वगैरह के बारे में बड़ी बात हो रही है कि स्टॉक प्रेडिक्टिव मॉडल्स और ये जो आपके दूसरी चीजें होती हैं, इंडेक्सेस होते हैं डिफरेंट, तो वी वांट टू प्रेडिक्ट दोस, तो इस पे काफी काम हो रहा है. Another thing that is extremely important before we start the convolutional network is momentum, and momentum is one of the better approaches to avoid overfitting. So for MNIST वगैरह you don't need momentum because MNIST is already solved. MNIST हो गया, CIFAR 10 data set हो गया, so I don't think so you will need to do momentum. Although CIFAR 10, the data set CIFAR 10 gives you maybe 70% accuracy on the test set. So there's still room for improvement, but for improvement you need a GPU. Otherwise it will take maybe 3 hours to get that model in place if you use the convolutional network, because there are so many images and they are complicated images. तो कोई दरख्त का है, कोई बंदे का है, कोई बोर्ड का है, etc etc. So momentum or SGD with momentum is a method which helps you to accelerate the gradient vectors in the right direction. So you can imagine if I am doing a gradient descent, then at each timestamp or at each instance, I always try to bring the ball downwards. ये तो अब clear है ना आपको concept. So, but the shape of the error curve can be very strange. You know, I might have a some sort of a trough. जैसे आप खड्डा कहते हैं उर्दू में, ठीक है? I might have some sort of a trough near a local minima. And if the SGD enters a trough, so it is going to slide down and go to the local minima. I don't want that to happen. So even though I want the ball to go down through the partial derivatives, I always want to go down by taking the resultant of all the directions or all the x's. But I still don't want to be in any trough which is near a local minima. So I do want to go down, but I want to have some momentum as well, so that I can jump if there is such a situation. Do you understand what I'm saying? So the only way I can avoid the local minima is through a jump. So I can jump from one part to the other, and then I will be able to avoid the local minima or that particular trough which is going to lead me to a local minima. So it turns out that momentum does help you immensely in avoiding overfitting, and also to help you get the convergence on track. So that is why it is one of the most popular optimization algorithms, and many models are trained using it. So you need to keep this in mind कि momentum हमने इस्तेमाल करना है, ठीक है? So it has to deal with, so just to give an example, exponentially weighted averages. So momentum होता क्या है, ठीक है? So let's give it a shot कि उसका formula क्या है. So we use the concept of a weighted average. Like if I have like 500 different things, and I want to approximate a sequence of 500 numbers. Sequence means कि एक के बाद एक आता है. There's a sequence to it, right? So there's a sequence of 500 numbers, but I say कि यार ये बहुत, I mean, if you take it too granular, if you want me to use all the 500 numbers, then that's going to take a lot of time. And अगर इसमें second trough आ गया बीच में, then I might fall into a local minima, or that falling into a trough will also waste my time, even if there is not a local minima. There is a trough. You can't call it a local minima, but there's a small trough. So the gradients will start to slide down the trough, and that is going to waste my time. I just want to jump it and continue my descent. ठीक है, क्योंकि वो trough तो is actually something strange कि, I mean, trough का मतलब ये है कि you can have something like this कि, so let me draw here. So I might have hundreds of x's in the while computing the partial derivatives. ठीक है, मेरे डायरेक्शंस तो बहुत सारी हो सकती है ना, जितने वेट्स हैं उतनी ही मेरे पास क्या होंगे, डायरेक्शंस होंगे. नहीं, कितने डायरेक्शंस होंगे? How many partial derivatives do I need to compute? As many weights as there. So that means as many directions. So for example, this is the error surface, and let's say I have something slides here and then goes back up, and this is some local minima, and then this is the actual minima. So if I am here at this point, right? So if I go down slide, so the gradient which is in this direction, the weight vector which is in this direction is going to slide down here. जब आप उसका partial derivative compute करेंगे, right? Because the impact is huge, so it's going to probably influence the other. So the ball is going to slide down. But if I have the momentum, then the resultant might be here because it will have some speed as well. What is momentum? Mass into velocity, right? So it's going to have some velocity, so it can potentially jump this and be here. So it will go up because it cannot go down, and then it is going to move here and probably stuck here, whatever. So this is the sort of situation जो कि we want to avoid. सही है? So if you, just to explain it, कि if you have the concept of this exponentially weighted average, सही है? So let me just yeah. So let's say कि we plot this ये data है, तो it's plotted just in 2 dimensions, and this is noisy data because you can see I can't fit a line to this data very easily. It's noisy data, ठीक है? So इस पे आप एक function fit करें. So the function goes like this. None of these dots share the x coordinate. So every x has a different y value. It is a unique number, and the x defines the index of our sequence. So if this is the sequence S, If this is the sequence S, then S is basically indexed by X. So if I have an X value, it is going to give me a value of Y. So it's a sequence of 500 numbers. Okay. Yeah, it's just a way of representing it. So इसमें problem अभी क्या है? The problem is के I am not able to learn a good function. I want a curve which fits it in a better way. So this is the normal fitting without momentum by using, let's say, a convolution neural network or whatever. Okay. So we want some kind of moving average. What's a moving average? Okay, like I have 500 numbers. So I say, okay, yeah, I take a window size of 10 starting from the first number, and I approximate those 10 numbers by one number. Just take the average. Or you can say weighted average, because why do you say weighted average? Because every point is not as important as the other one. So in mathematics or in this machine learning scenario, it's often you have to use the concept of weights. Maybe you will develop your own formulas in research. So whenever you develop a formula, इस पे भी हम एक student के साथ हम काम कर रहे हैं कि we are developing a formula in which we are bringing weights, and obviously when you bring weights, then you have to normalize. So weights are important because every variable is not as important as the other one. Sometimes one is important, some other important. So weighted. So I can approximate the sequence by, if I take a window size of 10, so 10 size approximate by one number taking the average and give it a weight. Move the window to the next 10 elements in. So this approximates. So this is similar to the momentum scenario. It helps me go faster and makes a jump. Because if I approximate, then I can jump. If I don't approximate, then I have to go to each and every number, and then I might slip and fall in the slide. अगर कोई slide आ रही है तो मैं उसमें fall कर जाऊंगा. But if I take an approximation, then I can easily jump over it. So the concept of momentum, behind momentum, is the concept of the weighted average of numbers, जो भी आपके पास training data में आ रहे हैं, ठीक है? So for example, if you apply momentum here, so you can see that it is trying to fit the data in a better way than the red line. So the error with momentum is going to be less as compared to the error with the original fitting without momentum. And ये almost always the case. वो आपको मैं assignment दूंगा अभी आज, जो आपका प्लेग्राउंड है ना, अभी आप CNN का प्लेग्राउंड बनेगा अब इंशाल्लाह, ठीक? तो अभी खैर हम I will see the blogs today as well, ताकि आप लोगों को थोड़ा सा वो you get the confidence. So I have singled out 4 blogs, so we'll go through those. सही है? Is this in clear? So instead of having a data with a lot of noise, we got a much smoother line which is closer to the original function than the data we had. Okay. So, and you can see the jumps here, right? Are you looking at the jumps? It's a bit zigzaggy sort of thing. It's because of that approximation, and the approximation is respect to the training data जो आपने उसको दिया हुआ है. So when the points are, it takes a direction. First it is going down, and then it is trying to follow. It's going up, and then almost it is following the red curve, but it's trying to do something else. Okay, trying to fit the data in a better way. So it turns out that if you approximate such a behavior over many epochs, then this turns out to be better than a fitting without momentum, and definitely it avoids overfitting, because whenever the neural network wants to overfit, it will run away. Neural network will try to catch the momentum so that it overfits, but momentum will simply run away, or it will keep the neural network running away from the overfitting scenario. So this is the scenario. This is how you develop the equation. So beta is a hyperparameter which you want to tune for the momentum. So you specify beta. Typically we take 0.9, because if you take less than 0.5, then the speed is slow of jumping, right? So छोटे jumps होंगे. If it is very close to 1, then the jump might be very high. So typically 0.85, 0.9, 0.85, 0.9, that is how it, and it does make a difference. ये हमने देखा हुआ है. Batch normalization will make a difference to you, and momentum will make a difference to your learning. Also the number of layers, वो तो खैर that's a different story altogether. We are approximately averaging over the last 1 divided by 1 minus beta points of sequence. So that is the interpretation. So 1 minus 0.9, 0.1, 1 over 0.1 is 10. So if beta is 0.9, you're approximating over the last 10 points. So the window size is 10. At each timestamp, you are approximating over the last 10 points and finding out the direction for the next one. G. It's a I told you ke I think last class mein ke the training data that you give, it has to be normalized with respect to some parameters ke you try to bring it in the same format. यानी कि जैसे स्टैंडर्डाइजेशन होती है ना, तो इट्स वन ऑफ द टेक्निक्स ऑफ स्टैंडर्डाइजेशन, तो वो डिटेल में भूल गया, आई विल टेल दैट टू यू इन द नेक्स्ट क्लास. ठीक है, उसकी लेयर भी अलग आप ऐड कर सकते हैं. सो ये फॉर्मूला एस इज द सीक्वेंस. सो द न्यू वैल्यू ऑफ वी इक्वल्स टू बीटा vt minus 1 plus 1 minus beta st. सही है, तो st is the original sequence that you are going for, and beta values goes between 0 and 1. So this is a typical way of creating a formula. Ji. This is applied on the input data while in the feed forward phase. नहीं, not like that. So here we can see that we can't use a very small value or a very large value, but just an average value like 0.9 or 0.85 is something which is okay. So beta equals to 0.9 provides a good balance. So when you take a small, that the fluctuation is going to be too much, that it is almost going to be equal to the noise. So we are closer to the noisy data. With bigger values, we get lots of jumps, so it's not what we want. So therefore, that thing, it works out for us. So momentum is the moving average of our gradients used for updating the weights of the network. So this V term that we calculate is used for, so it seems that it's happening at the back propagation stage. So whenever I update some weight vector, W equals to old W minus alpha. What is alpha? The learning rate, right? Into VT. To VT, or VT kya cheez hai? VT is this one in which I basically incorporate the momentum in the weight update equation. What was here actually जो हमने weight update equation पढ़ी थी hourly से पहले, W equals to W minus alpha into the change in weight. So ये I think this is the equation of the change in weight, this one. Okay, this delta L loss function is basically that, but now I'm coupling that up with momentum. So I might, the original value of VT can be start with 0, for example. So it's the VT which I use here in the weight update equation and not the original delta W. Okay, is this thing clear? So it is being used at the back propagation time. So the only thing is that I'm putting some restriction on the weight update equation, and that restriction is primarily defined by beta. Okay, tumne how much you have to update. So that's equivalent to the jump thing that we are talking about. How much you have to fluctuate, in fact, while going down. So momentum mein you can say that I am going down, but I am also doing like this. So I can either walk or I can either jump. I can go down, but I can walk or jump also. If I jump, I might go far, then that might be better for me. So it basically means that this equation is basically a new type of momentum. मुझे इसका नाम भूल गया. You might come across this Nostrov momentum or something like that. So this equation is a bit different. You can see here. So I incorporate alpha here, and then I simply subtract minus VT. So in some experiments, this might turn out to be better, but as far as your experiments are concerned, you are just going to use what TensorFlow offers you. So you don't have to code these things. अगर आप अपनी learning के लिए करना चाहते हैं, you can do it. Or if you want to go into deep learning research, then you can, then you should definitely code these on your own. अगर आप research में जाना चाह रहे हैं, ठीक है? Because then you might need to deep learning research is primarily based on discovering new types of architectures, new loss functions, and extensions to backpropagation mechanisms for your own applications. For example, you pick a domain like time series forecasting. The time series forecasting there's a lot of work that needs to be done. So people are designing new models, new hybrid models. They are designing new loss functions, new ways of updating the weights. Like this one is a new way of updating the weight based on momentum. So that's the what research is all about. Okay. SGD does not compute the exact derivative of the loss function. Why? Because we are on a mini batch. Mini batch can't approximate all the 1,000 instances that I have, right? 32 ka batch hai, 64 ka, that's nothing. So I can't say that I'm computing the exact partial derivative of all the weights, right? So that means that we are not always going in the optimal direction, because I'm working on a very small sample. It's like I want to survey the people in Gulshan Iqbal, but I take like 10 people and I make a conclusion. So if I, but चाहे मैं 10 के मुतादिद सैंपल ले लूं, still I am never approximating the original population. ठीक है? So in that case, our derivatives in each mini batch are somewhat noisy. ठीक है? So these weighted averages with momentum can provide us a better estimate, which is closer to the actual derivative than our noisy calculation. So the assumption is that ये जो हमने ग्राफ बनाया था कि we draw the red line which is noisy. ठीक है? So our assumption is that this is the same case for partial derivative. They are noisy because of the mini batch scenario. So if we use the concept of momentum after weight updates of each mini batch, right? So then that is going to help you recover from that noise somewhat. And if you do this for like hundreds of mini batches, so you are probably going to approximate the correct density. सही है? समझ में आ गई? So this is one reason why momentum might work better than classic STG. Remember, in deep learning there is no standardization, except the fact कि हम ये कहें कि ये problem है, use this algorithm. That's it. There is absolutely no standardization के to solve this problem, this is the ideal configuration that I should use. This is the amount of hidden layers I should use. This is the way I should program the whole methodology. There is no standardization. You can look up all the research papers and you can see that everyone is, hardly anyone is doing any gap analysis except those who are doing PhD. So there's so much space for research here that people are just cashing in on that. The other reason is ravines that I told you about. Ravines, an area where the surface curves much more steeply in one dimension than in the other. They are common near the local minima. Okay? And SGD has trouble navigating them. SGD can't handle ravines, in which in one direction I'm going down. So SGD will tend to oscillate across the narrow ravine, since the negative gradient will point down one of the steep sides rather than along the ravine towards the optimum. So SGD will not lead towards the optimum, rather it will start sliding down the ravine. And it will keep on oscillating there. फंस भी सकता है, right? So momentum will help you accelerate. So here in the left figure, it is sort of stuck because it has no momentum. So it's just walking. So फंसेगा, वापस आएगा, फंसेगा, फिर वापस आएगा. So it's just to and fro. So you might or might not reach the optimum unless you restart the whole thing. ठीक है? So I can't restart training, right? I'm training thousands of images. So if I see that the error function is growing constant after several iterations, I can't restart the process, right? It's not like going to a shop and buying something. It's a whole loop of work, and it might take hours to execute one code of deep learning if you don't have a GPU. So that's why momentum it can help you break away from that scenario. I hope that this concept is now very clear. Okay. So now we are on to this convolution neural networks designed to address image recognition systems. So there's a class of applications which are dealing only with images, and the most powerful application these days is the autonomous car or the autonomous vehicles that America में काफी research हो रही है इसके ऊपर. Tesla, I think, already has the cars on the road. Google has a car on the road since many years, and Google is again, they are working on to make it better and better. So it's all about image processing, because you got cameras at different points of the car, and based on those cameras you are just digesting the images, live video feeds in real time, and then you have to discretize those images binarize your images in real time and then process them. So the main algorithm which is being used for image processing is the convolution neural network. So Google has Google and many other people have done created convolution neural networks which are very complex, consisting of hundreds of layers and thousands to hundred thousands of parameters. For example, AlexNet, ResNet, VGGNet, DetectNet, UNet. So net, all of them are con nets. So there are many of them now. And I told you about transfer learning, right? So transfer learning, that's what is happening. So if I have a VGGNet, which is a very complicated algorithm and very famous, if I have a VGGNet which is already trained on images of, let's say, boats or ships or yachts, so I can download that model and use that for my own problem, because I cannot challenge the accuracy of VGGNet. I don't have that setup to set up a VGGNet. Okay, so it's very expensive, and if someone already has done it, so that is why the concept of transfer learning is created, because of deep learning scenarios. Okay, people want to do research, facilitate research. So if someone else has learned the model, then you give it. So when you work with images, then things grow very complicated because of the large number of parameters. And why does an image have a large number of parameters? Yeah, it's because of the number of pixels. So I'm bound to give hundreds of neurons in the input layer, and I should have at least that much neurons in the hidden layers. And my hidden layers are pretty complicated, so it generates thousands of parameters. So I have to learn the weights and biases in that way. Okay? So that's why. So convolutional networks is designed to address image recognition system. हमारे पाकिस्तान के अंदर as yet one of the best applications can be in banks, in which you can just recognize the checks. There are machines, जो कि जिसमें आप you can deposit the checks, but I don't know whether they are using this convolution neural network thing or not. So in real time, you can just show the image of the check, and it can detect everything, and clearing with the time lagega. So that's not what we want. So I don't know any tangible application right now in Pakistan, maybe, but I'm not that much connected with the industry right now. So there's a need to connect, in fact, now. So basically, images ke andar the problem is about classification. Like I told you at the beginning of the class, an image contains unnecessary information and noise. If you snap an image with this mobile phone, so that's not a professional high-speed camera, right? Like people used to buy high-speed cameras in the past. Abhi bhi karte honge jinko shauq hai. So that generates a very high-quality picture, which your meeting will end in 10 minutes. एक मिनट जरा ऑनलाइन जो स्टूडेंट्स हैं रुक जाए, मैं आपको दोबारा दूंगा. Stop share.